You have mastered Bayes' rule, transition matrices, and limit theorems. You know how to manipulate named distributions and calculate expected values in a vacuum. But an academic environment is sterile. A textbook gives you a neatly bounded word problem with a single correct answer at the back. The real world offers no such comfort. High-stakes domains like risk management, engineering reliability, and financial forecasting do not present perfectly packaged mathematical exercises. They present ambiguity. You are often handed raw, incomplete data, a vague business objective, and a tight deadline. You have to systematically synthesize that messy reality into a concrete, defensible action. Applied probability functions as a rigid end-to-end pipeline designed to transform raw information into quantified decisions. We structure this process through a sequential 6-stage pipeline. First, you frame the exact uncertain quantity you need to understand. Second, you choose a structural probability model that mirrors the actual mechanics of the problem. Third, you estimate the model's parameters using historical data. Fourth, you simulate that model forward to propagate thousands of possible future outcomes. Fifth, you quantify the exact uncertainty bands around those outcomes. And finally, you communicate that specific risk to non-technical stakeholders to drive a decision. Skipping any single step in this sequence transforms a mathematically rigorous analysis into a dangerous operational liability. Let's apply this pipeline to a tangible scenario. A large manufacturing floor relies on a piece of critical heavy equipment, and the team needs to know its risk of breaking down. Stage 1, we frame the problem by defining our exact random quantity of interest. In reliability analysis, we call this T, the time until the machine fails. The decision driving this analysis is strict. Management must schedule preventative maintenance before the risk of catastrophic failure becomes too high. Stage 2, we select our model. This graph displays an exponential decay curve, mapping out the probability that the machine survives as time progresses. We propose the exponential distribution to govern our variable, T. But this model choice comes with a severe structural assumption, known as the memoryless property. The math assumes the machine does not age. We can only justify using this exponential model if the physical failures are caused by sudden, random external shocks, like a power surge, rather than gradual, predictable mechanical wear over time. A chosen probability distribution must always match the physical, data-generating story of the real world. You never choose a model just because the math is convenient. Stage 3. Our abstract exponential model requires a specific parameter to anchor it to reality. This scatter plot shows historical failure times for similar machines. We use maximum likelihood estimation to fit a curve to these points, adjusting the shape until it locks in our failure rate parameter, lambda, at 0.0005. Practitioners must follow a strict rule here. You never report this fitted parameter as a solitary number without calculating its standard error. Stage 4 requires us to look into the future. When business environments become highly complex, theoretical equations often break down and fail to provide direct answers. We use Monte Carlo simulation as the bridge. By sampling from our fitted model thousands of times, we propagate the data forward into a wide spectrum of possible future breakdowns. Simulation turns a static equation into a dynamic, interactive map of operational risk. Stage 5. The most dangerous action an analyst can take is targeting a single, precise point forecast. This updated histogram reveals what decision-makers actually require, a prediction interval. These brackets define a calibrated band of plausible outcomes, capturing the true spread of the risk. We can deconstruct the uncertainty inside these bands into two distinct types. First is epistemic uncertainty. Epistemic uncertainty is born from our own ignorance, a lack of historical data, or an imperfect model. It is the only type of uncertainty we can actively reduce by gathering more information. Contrast this with aleatoric uncertainty. This is the irreducible randomness inherent to the physical machine itself. No amount of historical data will ever eliminate this core variance. The primary value of a quantitative analyst is cleanly separating the variables we can learn from the variables that are strictly random. Stage 6. Look at this equation. It is mathematically rigorous and entirely useless to a business leader. Technical output must be translated. We reframe the output into plain language. There is a 37% chance the machine survives past 2,000 hours. Stating a probability is not enough. A number in isolation does not trigger action. It must be paired with a business threshold. We attach a concrete directive. This falls below our 50% reliability target. We recommend scheduling preventative maintenance at 1,400 hours. Mathematical rigor succeeds when it is hidden beneath calibrated, actionable clarity. This matrix compares 3 entirely different industries. We used reliability as our template, but this exact 6-stage architecture dictates success across all quantitative disciplines. If your core question shifts to tracking adverse financial outcomes, the simulation workflow pivots to compute value at risk, identifying the exact threshold of potential capital loss. If predicting next month's product demand, you lean on central limit theorem approximations, but the requirement to deliver calibrated uncertainty bands remains identical. Whether tracking a financial threshold, a machine's lifespan, or next month's inventory, applied probability maps uncertainty so that leaders can finally make a choice.